Hello and welcome to this lecture. In this lecture, we'll be talking about the second order circuits. It is the chapter number 8 of our Sadiku's textbook, and topic for today is the step response of a series RLC circuit. So in this topic, we'll be seeing how we solve a series RLC circuit with a source. In our previous lectures, we have seen how we solve a series RLC circuit and a parallel RLC circuit without a source. So basically what is happening here is that we have a second order circuit which comprises of a resistor, inductor and a capacitor. There may be some charge that is stored in that capacitor. There may be some magnetization in the inductor, and when switching takes place, as we see here in our switch, that time t equals to 0, it may close, it may open. There is a source that is either involved with this circuit after the switching. So let's see how this sort of second order circuits behave and how we solve or how we develop the differential equations for these this sort of circuits and how we solve them. So first of all, we have a series RLC circuit. We have some initial voltage. We have the capacitor, and the voltage across the capacitor is given as V. The current that is flowing in this branch is given as I. And at time t equals to 0, the switch closes. And basically, after we can say that after time t equals to 0, the circuit looks something like this. So we have a plus minus source, we have resistance R, we have an inductance L, we have a capacitor C, and this is how our circuit looks like. And the capacitor voltage is given as V, and the current that is flowing in the circuit is given. So this is our circuit at after time t equals to 0. And if we have to develop a differential equation for this circuit, or if so, we just simply use the KVL and write down the corresponding equation. So our equation becomes Vs equals to IR plus voltage across the capacitor L times di by dt plus the voltage across the capacitor, we call it as Vc, or we can say it as Vc, right? So this is how we write the differential equation for this, and where we know that Vc is 1 by c integration of I d to dt, right? So this is how we write down this differential equation. Uh, and we have seen this differential equation in our previous lectures as well, and we developed our second order differential equations from this equation. So in this case, we also know that for capacitor current, so IC is given as, or the capacitor current is given as C times dV by dt. So using these two equations, this one and this one, so I call them equation number 1 and I call this equation number 2. Using these two equations, what we get is this: dv square by dt square r by l dv by dt plus v by lc equals to vs over lc. And remember, in our previous lectures, what we have seen that using both equations, since in our previous lectures we solved a series RLC circuit or a source-free series RLC circuit, and in a source-free series RLC circuit there wasn't any Vs. So in this equation looked previously, or in the previous lectures, looked something like this. And from this equation we developed our characteristic equation. Remember the characteristic equation. We developed our characteristic equation, and that equation was in the form of s equals to 2 alpha s plus omega naught square equals to 0. And we solved this equation and we found out that there are two solutions, s1 s2, and those can be given as minus alpha plus minus under root alpha square minus omega naught square. So this is what we have seen in our previous lectures, that how we solve a source-free RLC circuit. But here the situation is a little different, that we have a voltage source that is appearing here. So in that case, the solution comes out will have two parts. The solution will have a transient part and solution will have a steady state part. Remember that when we do not have a source, when Vs is not present in the circuit, our circuit only have the transient response, right? So it will only have a transient response. But when we have a voltage source connected to the circuit will have certain transients and it will have a steady state response. Or in an intuitive way, we can say that there were some initial conditions in the inductor and the capacitor. So when the switch was closed, what happened was that, remember, the inductor is given as L di by dt. It resists in instantaneous change in current. The capacitor is given by C dV by dt, or sorry, the inductor voltage, and the capacitor current is, and the capacitor resists instantaneous change in voltage. So there is some transient behavior that comes because of this two differential equation that appears in the modeling of a inductor and a capacitor. So once these initial transients dies out, or the circuit reaches a steady state value, and that is what it is represented by this part. So when we so what is the transient response? So for this circuit, that for transient response, what we do is that we have this differential equation. Remember this differential equation, uh, or for source free, remember, for source free case, we have Vs equals to 0, right? So for Vs equals to 0, this differential equation reduces to a characteristic equation of 2 alpha as, so s square plus 2 alpha s plus omega naught square equals to 0, right? So this is equals to 0. And if we solve this characteristic equation, we got three types of response. One was overdamped, remember? One was critically damped, uh, and the third case was underdamped. And remember the condition for them. So for overdamped, we saw that our alpha, the roots for the and before for the overdamped, we saw that there are the alpha is greater than omega naught. For critically damped, we saw that alpha is equal to omega naught, and for underdamped, we saw that alpha is less than omega naught, right? So this is the condition which we, or conditions which we saw in our uh, uh, source free case. And when we solve this thing for a step response, or a circuit, or a second order circuit which is having a source, these response corresponds to the transient response of the circuit. So whenever we are having, or we are left with a circuit or a second order circuit which is having a voltage source, so we can divide, we have to basically, and we are asked to find out the response for the circuit. So we have to divide the response into two parts. One part is the transient response and one other part is the steady state response. So the transient response, we can easily find out the transient response by using the by developing the characteristic equation and then finding out the values of alpha and omega naught. And from these conditions, you can easily find out whether the response is overdamped, critically damped, or underdamped. And remember, for an overdamped response, the voltage equation looked something like this: a1 e raised to power s1t plus a2 e power s2t. Similarly, for a critically damped response, and similarly for an underdamped response, the transient voltage or the solution for the differential equation looked something like this, right? So whenever we are having a circuit like this, we have, what is the first thing we do? We divide our response into two parts. One part is the transient response, the other part is the steady state response. So for the transient response, we develop the characteristic equation, uh, or we write the differential equation. From the differential equation, we develop the characteristic equation. From the characteristic equation, we use this condition of alpha and omega naught to find out whether our response is overdamped, critically damped, or underdamped. And from there, you have the relationships for all these three conditions, and from these conditions we can easily find out which is or how our voltage response will look like, or how our eventual voltage or whether current or voltage response will look like. Now for steady state response, how we are going to find it? So basically for steady state, it means the circuit has steady state response. So steady state response basically means that the so long time has passed for the circuit after switching, or remember the definition of time equals to 5 time greater than 5 tau is generally considered as uh, good for finding steady state response. Remember, this is more used in first order circuit. This is not technically a term for the second order circuit, but generally it means that your circuit has reached steady state. Whether there is an inductor involved, it means that inductor has either completely magnetized or demagnetized. If there is a capacitor involved, it means that the capacitor will be either completely charged or it would be completely discharged. So this is what it is meant by a steady state response, or we can also say that once the switch has been closed, it remains closed for infinite time. So basically what we have to do is that we have to find out the solution for this equation at uh, uh, after you can say after t equals to infinity. So after time t equals to infinity, this circuit will look something like this. So we have a voltage source, we will have a resistor, the inductor will be acting as a short circuit because it will be completely charged, and the voltage source or the voltage or the capacitor will be behaving as an open circuit because it will be completely um, sorry, the inductor will be behaving as a short circuit because it would be completely magnetized to the value of current that is flowing in the circuit, and the capacitor at time t equals to 0 will be behaving as a completely charged capacitor, and that capacitor and that basically would result in capacitor behaving as an open circuit. So what will happen here, that if we have voltage Vs over here, so this capacitor will after time infinity, this capacitor will charge to this source voltage because this is the driving source that charges this capacitor. And similarly the current that is I infinity that will be flowing through, or the inductor would have been magnetized, it would be current that will be given by Vs divided by R, and this current will keep on flowing till both capacitor and both these nodes will have similar voltage, then no current will be flowing. But at infinity it will behave as a uh, short circuit, and this will be the initial value of current. But at infinity, since this will be an open circuit, this value will be 0. So generally in this case we are not concerned with I equals to 0 because we are concerned with the voltage across the capacitor. Once we develop the voltage relationship for a capacitor, we can simply use V for all. We can use V of t, and remember, if we differentiate this, we will get current through the capacitor. So if we have to find out this value of current, we'll just simply differentiate this thing, the voltage response multiplied with the capacitance value, and we'll get the current that is flowing through the circuit. Right. So this is how we find out the response. So now we have seen transient and steady state response. So the final solution, again, it will be the linear combination or addition of both the transient response plus the steady state response of the circuit. And remember, once we have these response, it will look something like this, and the values of A1 and A2 are calculated with the help of the initial conditions. So if this is a series circuit, we'll be given some initial condition or initial values for voltage um, uh, across the capacitor and the current through the inductor, or the initial condition will be uh, on and specifically in this case, we need these two initial conditions uh, to solve this completely for values of A1 and A2. Similarly, we will be seeing that in case we are given a parallel RLC circuit, in that case, we'll be requiring the initial conditions for current, um, both I of 0 and di by dt at time t equals to 0, just as we have seen in our previous lectures where we talked about the source free series and parallel RLC circuits. So now let's solve an example and see how this thing is done. So this is example 8.7 of our textbook. And remember, we are following Alexander Sadiku's textbook for this part of the lecture. So again, it says that for the circuit shown in figure 18.8.19, find V of t and I of t for time t equals to 0. Consider these circuits, these cases r equals to 5, r equals to 4, r equals to 1. So we are given this circuit, and in this circuit, they have given us three cases for r equals to 5, r equals to 4, r equals to 1. So we basically have to find out all the three cases. So for simplicity, we'll be solving for r equals to 5 in this example. I leave r equals to 4 and r equals to 1 for you to solve. Again, the method will be the same, just there will be a little bit difference. And I hope that the previous 3 slides will help you in finding out what exactly would be done. So again, first of all, again, we have to find out the voltage and current I. So this is the current I we have to find out, and this is the voltage we have to find. So first of all, we have to draw the circuit before t equals to 0. Remember, we are not given specifically given any initial condition, so we have to find out the initial conditions. So we first of all, before it means that if we have to find out the initial conditions, we have to basically find out the condition of the circuit just before switching off. Before t equals to 0, the circuit looked something like this. This is 24 volts. This is my resistance R, and I have taken it as 5 ohms. This is my inductor. This is my capacitor, and this is the switch. This is R equals to 1 ohm, and this switch was closed. So this switch was closed. This inductance was 1 Henry. So now we have to basically find out what will be the value V of 0 negative, or what will be the value of voltage that will be appearing across this capacitor. And so this capacitor is in parallel with this 1 ohm resistor. So remember, this circuit is in this condition since time infinity. So the equivalent circuit would look something like this. So the inductor would be completely magnetized, capacitor will behave as an open circuit, and there will be resistance 1 ohm. There is 5 ohms, there is this 24 volts, and this case. So this is the VC at 0 negative. This value of current will be IL 0 negative. So let's find out both values. So VC 0 negative will be simply the voltage that is appearing across 1 ohm. So 1 ohm divided by 1 plus 5. Remember, the only resistance in this path are 5 ohm and 1 ohm, multiply by 24. So this is 4 volts. Similarly, IL 0 negative. So if I have to find out the current through this inductor, so this current will be 24 volts divided by overall path resistance 6 ohms. So this is 4 amperes. So these two will be my initial conditions for this case. Okay. So now I have found out my initial conditions, and I know that for capacitor, remember, again I will write the differential equation first. For the capacitor, it is IC C times dV by dt, and the variable that comes with the differential sign, it means that it doesn't change instantaneously. The voltage across the capacitor doesn't change instantaneously. So VC at 0 negative will be VC at 0 positive. So we can call it as VC 0 equals to 4. Similarly, inductor, for inductor, uh, just simply use IL 0 negative, IL 0 positive equals to IL at 0, and this is 4 amperes. So remember, for an inductor, you are given as V inductors L times di by dt. So since this I is the variable that comes with a differential sign, it means that it doesn't change is instantaneously. So now we have calculated our initial conditions. So initial conditions are voltage 4 volts, IL equals to 0 volts. Oh, sorry, IL equals to 4 amperes. So now let's move ahead and see what else we got. So even before moving ahead, we also have to find out the conditions for dv by dt, right? At time t equals to 0. This is basically our second, you can say, condition which we need. So in this case, so after this is, I will do this on the next page. So for dv by dt at time t equals to 0, this is our second initial condition. So for this, we know that uh, just after switching uh, the just after the switching, the circuit will look so for our second initial condition, we have to find out the dv by dt part. So for this, basically we have to see what happens initially just after, you can say, after t equals to 0, just after the switching. So just after the switching, we know that the current in the capacitor, in the inductor, doesn't changes instantaneously, and the voltage across the uh, inductor doesn't change instantaneously. But we also know that uh, current through the capacitor will change instantaneously, will change, and that is given as C times dV by dt. So at so if we have IC at t equals to 0, uh, C dV by dt at time t equals to 0, we can just simply find out this value by using this. So IC, so we know that the inductor will not allow the current in the circuit to change instantaneously, and the capacitor will not allow the voltage to change instantaneously. Yes, the current and voltage will change over time, but just at that start of an instant, the values will remain as such. So I see the current in this capacitor will be, or the inductor will be, the component which is forcing that current to stay at that level. So I see this is the value which we find out earlier, which was 4 amperes. So this it will be this value, and the capacitance value is 2.25 farads, and we can just simply find out the value of dv using this. So 4 divided by 0.25 is equal to dv 0 dt, and this value, so this becomes our second initial condition, will be 16. The value of dv by dt will be 16. So now we have both of our initial conditions. uh, First case was 4 volts, this is volts per second. So these are will be the two uh, initial conditions which we'll be using to solve this circuit. So now moving ahead, now we basically draw the circuit after t equals to 0. So what the circuit will look after time t equals to 0, the circuit will look something like this. So this is the capacitor, the inductor, also this is basically the uh, that is 24 volt, 5 ohms, this is 1 Henry, and this is 0.25. farad. This is the voltage V. This is the current I. So this is basically a series RLC circuit, right? So this is a series RLC circuit. So we know that for such a circuit, we first have to find out the value of alpha. We have to find out the value of omega naught, and from this we have to see what is the relationship between these two. So the alpha for this circuit, alpha is R divided by 2L, and omega naught is equal to 1 by under root LC, right? So if we find out the value of alpha, 5, 2 multiplied by the value of inductance, so this is 2.5. Again, this is seconds minus 1, omega naught, uh, 1 by under root 1 into 0.25. So if I find out the value of omega naught, this comes out to be 2 radians per second. So if I see from here, my alpha is greater than omega naught. So if my alpha is greater than omega naught, my characteristic equation will look s square plus 2 alpha s plus omega naught square equals to 0. My solutions will be s1 and s2 will be minus alpha plus minus under the root alpha square minus omega naught square. Alpha is 2.5 minus plus minus under root 2.5 square minus 2 square. So my two values of S1 and S2 will be uh, S1 and S2, the solutions. S1 will be minus 1, S2 will be minus 4. So these are real and distinct. So remember, in such a case, when alpha is greater than omega naught, the roots are real and distinct, and response, remember that this response or the transient response is what? So either it is overdamped, it is underdamped, or it is critically damped. So this response is actually overdamped response. Overdamped response, right? So now let's further solve it. So for overdamped response, so for overdamped response, and remember we are solving for this voltage. So for overdamped response, the voltage is given as A1 e raised to power s1t plus A2 e raised to power s2t. This is the transient case. And for total response, this is V transient plus V steady state, right? So for steady state response, we have to find out after t equals to infinity. So what happens to the circuit after time t equals to infinity? So after time t equals to infinity, this is 24 volts. This R equals to 5 ohms. This inductor will be completely charged. It means that it will behave as a short circuit, and this capacitor will behave as a open circuit. It will be completely charged again. So again, an inductor will be completely magnetized. The capacitor will be completely charged. So we see at infinity will be equal to, so this will behave as open circuit. It means that it will be charged at this node voltage. So there will be no current flowing. So I infinity will be 0. VC infinity, it will be 24 volts. Okay, so my V steady state, this will be the V steady state value. So my overall response, our overall response will be Vs, V or V steady state, that is 24 plus A1 e power S1t plus A2 e power S2t. So put in the values of S1 and S2, our response will be V24 plus A1 e power minus t plus A2 e power minus 4t. So this will be my response or overall response. Now we have to find out the values of A1 and A2. So for A1 and A2, we have to use initial conditions, right? So use initial conditions. My first initial condition, v is 0 equals to 4 volts. So just v of t 24 plus a1 e raised to power minus t plus a2 e raised to power minus 4t. Now put t equals to 0. So this thing becomes 4 24 plus a1 plus a2. So this comes out to be minus 20 equals to a1 plus a2. This is your equation number 1, right? Now using the this is, I call it A, call it B. Using the second differential initial condition, this is 20. Oh, sorry, this one was 16 volts per second. So this one was 16, right? So this one was 16. So just simply differentiate the voltage function. So we just simply differentiate the voltage function and see what we get here. So we just simply differentiate. So we get dv by dt. 24 becomes 0 plus minus a1 e raised to power minus t minus 4 a2 e raised to power minus t, right? So this is what we get. Now put t equals to 0, it becomes 16 minus a1 minus 4a2, right? So this is my second differential. Sorry, this is my second equation. Now solving equation 1 and equation 2 simultaneously, we get a1. So I leave this simultaneous solving of simultaneous equations for you to solve for yourself. It becomes a1 becomes 64 by 3 and a2 is 4 by 3. So my a1 and a2 becomes this. So my voltage function will look as 24 minus 64 by 3 e raised to power minus t and plus 4 by 3 e raised to power minus 40. So this is how the voltage waveform or will look like, and basically we have to find out v of t. This is how v of t will look like. Now our second case is find I of t. Remember, so this is the capacitor voltage. So this voltage is capacitor voltage because we are solving it for this one, right? So we have the capacitor voltage with us. We know that the current in the circuit is given as this I, and I is C times dV by dt. So this I will be the current that is flowing through the circuit, because the series circuit, the current through the capacitor is the current through the inductor, and this is the current through the resistor as well. So this is what we have to find. So this is C dV by dt. Just multiply uh, by C, the derivative of the voltage. So we get I of t. C is again 0.25, and we multiply it by, the derivative of this is 0. Minus becomes plus 64 by 3 e raised to power minus t, and this becomes minus 16 by 3 e raised to power minus 40. And if we multiply it by 1 by 4, so I of t will be so 64 divided by 4, it will be 16 by 3, 16 by 3 e raised to power minus t, uh, and minus 4 by 3 e raised to power minus 40. So this is the value of current that what we have to find, right? So now basically we have found out both values for current and voltage in the circuit once the switching takes place, and this is how we basically solve these sort of equations. So In the next part, basically we are asked to find out for or solve for r equals to 4, and similarly we have to find solve for r equals to 1. So remember, I'm skipping many steps. For simplicity, r was equal to alpha was equal to this value, and alpha in this case was equal to again r by 2l. So alpha will be 4 divided by 2, alpha will be equal to 2, and alpha in this case will be 0.5. So in the and our omega naught will remain the same. It will be 2 radians per second. This is second minus 1. This is again omega naught 2 radians per second. Remember, omega naught is equal to 1 by under root LC. So in this case, alpha equals to omega naught. In this case we have alpha less than omega naught. So this is the case for, remember, critically damped, and this is the case for uh, underdamped response, right? So in this one, we will have V of t will be equal to Vs plus, for critically damped response, my equation looked A1 plus A2 t e raised to power st, right? This is how my equation looked like. And for this case, my response, overall response, steady state Vs plus, uh, remember, this is where we have this imaginary part of the solution in the characteristic equation coming up. And for this one, we have, you can say, e power minus alpha t a1 cos of omega d t plus a2 sine of omega d times t. So this is how the solution looks like. Again, you have to find out initial conditions. Initial conditions, again, v of 0 and dv 0 by dt. Remember, so if we have to solve for r equals to 4, so this is 4 and 1, so v of 0 will be 1 divided by 1 plus 4 into 24. So 24 divided by 5 will be your v of 0, and similarly c times dv by dt equals to I, uh, and I of 0 will be, um, just after switching, I of 0 will be uh, what so if this is the circuit, we found out the I of 0 previously, this and in this case we have I of 0, 4 plus 1, again 24 by 5. So this will be the I of 0 in this case, uh, and this value is 4.8 amperes. So we have V of 0 as 4.8 volts and I of 0 as 4.8 volts. C times di by dt, so 4.8, so dv 0 by dt, this will be I of 0 divided by c, so 4.8 divided by 0.25 will give you the value of d by dt, and this becomes equal to 19.2. So in this case, we have 4.8 volts and 19.2 volts. And for this case, we have V of 0. V of 0, if we have to calculate V of 0, we have this value equals to 1. So V of 0 will be equal to 12 volts, because 1 divided by 1 plus 1 multiplied by 24. Sorry, not 124, it is 24, and this is equals to V of 0, and this is 12 volts. And similarly, dv by dt. That comes out to be I of 0 divided by c, and I of 0 in this case again is 12, and 12 divided by 0.25, and this value is 48 amperes per second. So this is volts per second, so dv0 by dt will be 48 amperes per second. So remember that not only if we change the resistance of a series RLC circuit, what happens is that the response or the transient response of the circuit changes. There is no effect on the steady state response. The steady state response for all these cases remains the same. But what we see is that some of the observations which we saw, if we change R. So if we change R, we see that transient response changes, right? Transient response changes, steady state response remains same. So we see that there is no change in a series RLC circuit. If we keep on changing the value of resistance, the steady state response remains the same. Um, so what basically it shows? It basically shows that if we want to control or a circuit like this, so if our value of resistance is low in this particular circuit, we'll have a underdamped response. So an underdamped response will look something like this. So this circuit will uh, a step function. So at time t equals to 0, we have applied a 24 volts step function here. You can consider it like this. So initially for r equals to 1, so the response would be something like this till it dies down. For r equals to 5, the larger value of resistance r equals to 5 is this, something like this. This will be for r equals to 5, the over damped response. So I call it for r equals to 5. This one will be for r equals to 1 ohm. So for r equals to 4 ohm, the critically damped would be something like this. So this response is r equals to 4 ohms. So basically how it shows that if we so our basically circuit settles down after some time to the steady state value, uh, uh, but it takes some time. So if we change or at time t equals to 0, the you can say the initial conditions or the inertia of the system immediately changes, and a 24 volt step input was applied. So the the system follows the step input, and it will take some time to system to reach its steady state. So in case we have a very low resistance, the system will basically have an underdamped response, and it will overshoot, and there will be some ripples until it uh, you can say dies down and approaches the steady state. If we have a very high resistance, it means that the system is overdamped. So it means that it will take some time to reach steady state, but there will be no overshoot. And if resistance is 4 ohms, it means that it's critically damped. So it means that it lies um, so at a certain instant that if our I mean it's a sort of a more or less perfect sort of alignment, that if we push the value of resistance below 4 ohms, we'll start having some sort of oscillations or ripples, which we see here. So interestingly, on a systems level or in a control systems aspect, there are certain cases where we need these ripples, but ideally a critically damped response is where the systems are mostly designed. They are not because in case of you can interestingly you can see this example as a example of a car moving across a speed breaker. Uh, So this considered this speed breaker as a 24-volt thing, and the car is having a certain inertia because it is moving with a certain speed and some. So what happens when a speed breaker comes? You apply a brake, so that brake basically uh, uh, or the intensity of that brake basically changes the response of your car. So your car basically approaches almost a dead speed uh, until you press the accelerator again and move ahead. But if you're not going to so you can consider it like this. So if you uh, press the brake optimally, your car will just simply smooth over or sail over the speed breaker. If you press the brake a little harder, the it will take some acceleration, it will take some energy for the car to move over the time, or it will take a little more time. But if you press your brake less than optimal value, you'll feel a bump, or you'll feel some jumps while passing over the speed breaker. And this is what exactly these curves would, you can say, would reveal. So r equals to 1, it means that your brake is less than the optimal that brake that is required, so the passengers will feel some oscillations there. So r equals to 5, it means that you have applied more than the optimal brake, so your car will reach the speed breaker or the ideal speed of 0 till you accelerate more, but it will take longer time. But if you uh, applied optimal brakes, you will just reach in a good time, you'll feel no oscillations, and overall the thing goes good. And this again happens in circuits as well. This is a phenomena, you see these oscillations especially in power systems, where you have your transmission lines. In case of a lightning strike, what happens that your transmission lines actually behave as have a very dominant inductive and capacitive properties, as well as the resistance for the lines itself. So they are basically a type of second order circuits, but there are some advanced concept that comes into play, or the transmission line theory comes, or the antenna effects that comes into play on that level as well. But overall, generally, you can say that the concept remains the same. The line have certain inertia, and in case of certain lightning strike, um, there is some voltage surge or a voltage spike, or for example, if you can say that there is a certain source that comes in contact with the lines. So we basically design in such a way that we do not have these sort of overshoots. And even if we have a certain overshoot, that overshoot dies pretty quickly, or this sort of surge is should not be coming in the system. But yes, there are certain cases where we need such um, you can say surge, because we need a certain change in voltage, or a rapid change in voltage, or a high voltage at certain instances. But again, it depends upon the certain applications for that. So here I stop my this lecture of series RLC circuit, and for or the response of a series RLC circuit in case of a step input. So in our next lecture, or in our next part of this video, we'll be talking about the step response of a um, uh, parallel RLC circuit. So thank you very much.